Hello everyone, welcome to the course on Introduction to Chemical Thermodynamics and Kinetics. We will first begin with the properties of matter. Now you know matter can exist in different phases. For example, the phases are solid phase, liquid phase, and gas phase or vapor phase. Now what is the definition of a phase? A region of uniform chemical composition and uniform physical properties. By that, what we mean is, consider a liquid in a sealed container. Now the liquid is in equilibrium with its vapor. Now if you ask what is the density at two different points inside the liquid, these two densities must be equal. So that is the meaning of uniformity. Similarly, the densities at any 2 points in the vapor phase will also be equal. However, the densities in the liquid and the densities in the vapor phase will not be equal, which means the liquid phase and the vapor phase are two different phases. Now the next thing is what describes the state of any macroscopic system. By state, we mean a condition of the system at a specific time, of course, because we are talking about time independent properties, that is fully characterized by values of a suitable set of parameters, and these parameters are called state parameters or state variables. Now the common state parameters are pressure, which we denote as P, temperature, which we denote as T. Usually by temperature we mean the absolute temperature, and the volume, which we denote by V. Instead of volume, we'll frequently use molar volume, which is volume of 1 mole, and we'll denote it by a bar. So V bar is nothing but the volume per unit mole, where N is the number of moles. Now let us first start a discussion on the gaseous phase or the vapor phase. Now you know that there is a celebrated gas law which is known as ideal gas law. Of course, by ideal we mean it is an idealized concept, and no gas or no real gas strictly follow ideal gas law. Now why we need a gas law or something like an equation of the state? In order to understand the relationship between different state parameters, we need this equation of state that will completely characterize the properties of the state. You have learned Boyle's law, which states the pressure is inversely proportional to the volume at any constant temperature. So we can write pressure is inversely proportional to volume at constant T. If we plot it, the pressure versus volume curve looks like a rectangular hyperbola, which we call as an isotherm because it is taken at a constant temperature. Now we can have several isotherms at different temperatures. For example, here I am drawing two different isotherms at two different temperatures, T1 and T2, where T2 is a higher temperature than T1. Similarly, you can ask what is the relation between the other two state parameters, volume and temperature, and that is given by Charles' law, which also you studied. According to the Charles' law, the molar volume is proportional to the absolute temperature. If we plot it, we'll get a linear curve like this. We can extrapolate the curve to get a concept of absolute zero of temperature. Now this law is valid for a constant pressure. So similarly, just like Boyle's law we can draw at varying temperature, we can also plot the Church's law at varying pressure. So here I have plotted the Church's law at two different pressure, P2 and P1, where P2 is greater than P1. Combining the Boyle's law and Church's law yields the ideal gas law, which is where R is the molar gas constant. In this case, we have also used the concept provided by Avogadro. We could also write the equation in the other form, which is PV is equal to nRT. So this is ideal gas law. This is nothing but an equation of a state for ideal gases. Now what about real gases? How do they behave? Before we discuss the real gas, let us ask a question. Here, when I plotted the Boyle's law or the Church's law, we showed that for Boyle's law, the isotherms for two different temperatures. Similarly, for Church's law, we plotted the isobars for two different pressures. But can we plot the equation of state, which is PV equal to RT, by varying pressure, temperature and volume simultaneously? What is shown here is an surface for an ideal gas, which is known as pressure, volume, temperature surface. Now any point on this surface represents or satisfies the equation of state, which is the ideal gas law. If a point lies outside this surface, that point does not represent a state of an system which obeys ideal gas law. Now the interesting thing is that if you have this surface, you can readily deduce the Boyle's law or Church's law. For example, Boyle's law is variation of pressure versus volume at constant temperature. So if you fix a particular temperature as shown in this figure and take a slice along this temperature, you will see an isotherm that represents the Boyle's law or isotherm at that temperature. Similarly, you can also recover the volume versus T, which is the Church's law, the isobar of Church's law, or the isochore, how pressure varies with temperature, from this three-dimensional curve, which is a surface in this case. Now let us discuss how real gases behave. As you know that ideal gas equation was a hypothesized version, meaning no real gas will show ideal behavior except for certain conditions that we are going to discuss. Now the question is, what are the deviations that we observe experimentally when a real gas is pressurized? Any gas under sufficient pressure forms liquid and eventually the liquid forms solid. However, the ideal gas law does not predict it. If you remember your pressure volume isotherm, it always predicts that even at very high pressure region, there is no change from gas to liquid, or there is no phase transition. But phase transition happens in reality. We'll first discuss few experimental facts that showed the deviation from this ideal behavior. One of the first experiments were carried out by Amagat, who gave the concept of compressibility factor. The compressibility factor, which we denote as capital Z, is defined as the ratio of the volume of a gas or real gas to the volume of the ideal gas. Now, using the ideal gas equation, this relationship becomes Amagat studied various gases and he plotted the compressibility factor Z as a function of pressure, and the plots look like this. For an ideal gas, of course, the compressibility factor will be 1. For many gases, Amagat found that they behave very differently. Like some gas, the slope of the curve is always positive. For some gas, there is a dip initially followed by a rise. If we plot the compressibility factor for the same gas at different temperatures, we get a very interesting behavior. Here I have drawn the compressibility factor at 3 different temperatures, T1, T2 and T3, where T3 is a higher temperature than T2 and T1. Now you see that there is a region where the curve more or less follows the ideal gas curve. Also note that this region is only when the pressure is almost 0. The temperature at which this behavior is observed is known as boil temperature, which we denote as T suffix B. So in this case, according to this drawing, T2 is the boil temperature. Here I show few real experimental curves for compressibility factor as a function of pressure. Now you see here on the left hand side, the plot shows the compressibility factor or the variation of compressibility factor as a function of pressure for different gases. You see for hydrogen, the slope is always positive. This was taken, all data were taken at 0 degree centigrade or 273.15 Kelvin. However, for methane, there is a dip followed by a rise, and the horizontal straight line shown here denotes that for an ideal gas or a perfect gas. The right hand figure shows the same compressibility factor as how it varies as a function of pressure for a particular gas. In this case, this is carbon dioxide, and as you see that high temperature, the slope is positive. At low temperature, there's an initial negative slope followed by positive slope, and right at the boil temperature, the curve merges with the perfect gas or ideal gas curve, but only in the region of very low pressure. Now we'll discuss another experiment where the pressure volume isotherms were recorded. This was done by Thomas Andrews, where he carried out a set of experiments with different gases and found the isotherms for different gases. Let us schematically draw how the Andrews curves look like. As before, it is an isotherm, so it's a pressure volume curve, but the nature of the curve is very different from what we see in the ideal gas behavior. Now here I plot the pressure volume curve at different temperatures. I chose 5 different temperatures, and as before, T5 is the highest temperature and T1 is the lowest temperature. Now let us first talk about the isotherm at T1. Now look at the shape of this curve. Let us also label the points or label the entire curve as A, B, C, D. Let us first look at the region which is the CD region. This region occurs at a low pressure where the volume is very high. Here the gas behaves ideally. So we can write the equation of state as PV equal to RT, but only for this region. Now note that if we want to change the volume by a certain amount, we have to apply a little pressure in this case. However, this is totally opposite for the case in the AB region, which represents the liquid state. Here, if we want to change the volume by the same amount, we have to exert huge pressure. The reason being, liquids are far less compressible than gases. The region in between, which is the BC region, represents an equilibrium between the liquid with its vapor. So this AB region represents the liquid and this CD region represents the vapor or gas. So following this discussion, it is now clear that ideal gas law will be obeyed only when the pressure is very low. So we can write or we can modify the notation for the ideal gas equation that it would be valid only in the limit of very low pressure. Now let us focus on this BC region where the liquid is in equilibrium with its vapor. Now note that as we increase the temperature, the region of volume over which the liquid vapor equilibrium occurs, that decreases. And finally, it reduces to a particular point. So if we draw a line which connects these regions, we'll get a region where the liquid is always in equilibrium with its vapor. However, this region shrinks as we increase the temperature. Now above this temperature, which is T4 in this case, the substance or the material always behaves as gas. So this point in the isotherm is called as a critical point, and the corresponding temperature at which the critical point occurs is known as critical temperature. So the ideal behavior is also observed above the critical temperature, where the substance is present always in the gaseous form. Therefore, we can say that the ideal gas behavior is obeyed for any real gas as long as either the pressure is low or the temperature is very high, which is above the critical temperature. Here I show some real experimental data for the liquefaction of the gas carbon dioxide. As you see, the location of the critical point is here and the corresponding critical temperature is 31.04 degrees centigrade. The shaded region, which is colored in blue here, denotes that in this region of the isotherm, the liquid is in equilibrium with its vapor. Now so far what we have discussed is that we said that for real gases, a departure or a deviation from the ideal behavior is observed, and that was experimentally verified by Amagat by measurement of the compressibility factor, and also by Andrews by measuring the real gas isotherms. Now in order to explain the deviation or departure, we need to devise a model for a gas which can satisfactorily explain the non-ideal like behavior of real gases. The first such model was put forward by van der Waals, who actually waived two crucial assumptions which we made in the ideal gas equation when it was formulated from the kinetic theory of gases. These two assumptions are, for example, consider a container. The ideal gas law will be obeyed if the size of the molecules are vanishingly small or the molecules are point-like objects. So there is no finite size for the molecules. Secondly, any intermolecular interactions between molecules were ignored. Now van der Waals made a correction to both these assumptions. Let us see what is the treatment that van der Waals made. The first thing van der Waals did is to consider the finite size of molecules from point-like objects to something like a hard sphere. Now imagine a situation: we have a container. If the molecules were all point-like objects, the volume of the gas will be equal to the volume of the container itself. However, if each molecule is supposed to have a finite size, then the situation will be very different. Now for 1 mole of gas, the number of molecules are fixed, which is Avogadro number of molecules, and so the volume or the total volume of Avogadro number of molecules will also be constant for a particular gas. So van der Waals said that the actual volume or the real molar volume, which will denote simply as V bar, will be more than the ideal gas volume by an amount which is constant in this case, because we are considering only 1 mole of gas, and this constant he denoted as B. Now of course this constant will be different for different gases. For example, methane will have some value of B which is different from the B for carbon dioxide. For n mole of gas, the volume will be simply, or the increase in the volume will be simply n multiplied by B. So this was the effect of the finite size. Now the second thing which van der Waals took into account is intermolecular interactions. Now let us discuss how that affects the total pressure of a gas. As before, consider a container and consider a particular molecule at the center of this container. Now this molecule is surrounded by many other molecules, and all of them are attracting this molecule. However, for a system at thermal equilibrium, this distribution of molecules inside the container is isotropic, so this molecule will feel equal attraction in all directions. So there will be no net attraction in any particular or any favored direction. So if this molecule moves, there will be no change in its velocity in a particular direction, and it will more or less obey the ideal gas behavior. However, the pressure of a gas is exerted when it strikes the wall of the container. Now let us consider when this molecule starts moving and tries to hit the wall of the container. Now when this molecule hits the wall, at that instant it is also attracted by the molecules which are near the surface and also by the molecules which are in bulk or inside the container. Now, since the number of molecules near the surface are less than the number of molecules which are in the bulk, there will be a difference in attraction. The attraction will be more from the molecules in the bulk because they are just large in number. So the speed of this molecule will be slowed down, and as a result, the molecule will strike with a less force on the wall, or the pressure will be reduced. Now we can mathematically formulate it. In order to understand that, let us consider on what factors this pressure will depend on. Now the definition of pressure is force per unit area, which means it will depend on how many molecules are hitting this surface of unit area per unit time. Now this number is of course proportional to the density of the molecules, or how many moles of molecules are present per unit volume. Secondly, these molecules are also attracted by the molecules which are present in bulk. So it will also be proportional how many molecules are present in the bulk. That number is also proportional to the density of the gas. So together, the pressure or the reduction in the pressure will be proportional to the square of density. And since density is inversely proportional to molar volume, it will eventually be inversely proportional to inverse square of molar volume. So, as before, we can write a correction for the pressure. The real pressure, which we just simply denote as P, will be less than the ideal pressure by an amount which is proportional to 1 over molar volume square, and this proportionality constant we call as A. And as before, A will be different for different gases. Now if we combine this pressure expression and the volume expression for real gases and put it in the ideal gas equation, which is P ideal into V ideal is equal to RT, and if we replace it by the real volume and the real pressure, we get the van der Waals gas equation, which is so this is the famous van der Waals equation in the molar volume form. If we have, or if we convert the molar volume into the actual volume, the equation will be just P plus n square A by V square into V minus NB is equal to nRT. We can use either of this equation, but we'll mostly use this equation in the molar volume form.